Hello, and a big welcome back to the Resources Conservation and Recycling webinar program. My name is Mitchell Jones. I'm the Outreach Editor at Resources Conservation and Recycling. It's wonderful to have you all with us today, along with Dominik, of course, our guest for today. So before we kick things off, I will just provide some introductory notes on the program, as I always do. So this is the English language version of the Resources Conservation and Recycling webinar program. We also have a Chinese language version of this program with Chinese speakers. If you are interested in that program, then be sure to also check that out. This program is run at 10 o'clock a.m. Pacific time every second Thursday. Now, the scope of this program matches that of the journal. And we also aim to run a balanced program. So you can expect to find all of the elements of the scope of resources conservation and recycling, the journal, represented equally in this program. We don't have any particular weighting for any particular aspect of the scope. We try to keep it very balanced if possible. The only thing that we do ask is that our speakers please try to make their presentations accessible as possible to everyone. We do have some breadth in our scope. Yes, we are quite a themed journal, but there is some breadth in our scope, and it can be that we are inviting or having audience members joining us that may potentially not be specialists in the topic of the presentation, and they benefit from reduced use of jargon, reduced use of field-specific terminology, and some basic introductory content to provide some background and context for the presentation prior to the actual nitty-gritty details being presented. Now, registration for this program is necessary if you would like to participate in the Zoom environment and also be able to ask questions, etc. You can register using the links that are provided in the Resources Conservation and Recycling newsletter that's circulated at the end of each month. You can also find the links for this program to register on the official social media pages of the journal. So if you visit the social media page for the journal on X, on LinkedIn, on Facebook, you will also find the links for registration on those pages. Additionally, you can also find them on the journal homepage. So if you visit the Elsevier journal homepage for Resources Conservation and Recycling, you visit the About tab, and you click webinar calendar, you will find the links there for upcoming webinars where you can register, in addition to a full list of all of our previous speakers and a link to their archived webinar on YouTube. All of our content is archived to YouTube. You can also view this program live on YouTube. It just means that you won't be participating in the Zoom environment with us and are able to ask your questions, etc. You can visit the YouTube page. It's youtube.com/@RCR journal. The final point that I want to touch on is we do really appreciate your feedback on the program. We want the program to suit your needs, suit your preferences. You have the opportunity today, as everyone does at the end of every webinar, when they're participating in the Zoom environment, to leave some feedback. You will be presented with a survey when you close your Zoom today. It's just a handful of questions, won't take you more than 1 to 2 maximum minutes. And we do take your feedback very seriously, and we use it to improve the program to better suit your desires and your preferences. Okay, so I'm going to share my screen now, and I'm going to try not to stuff it up like I did last week. Not last week, the last version of the event that we ran 2 weeks ago. It was the first time I made the mistake of sharing the wrong window, but I think I've got the right window this time. So the event program for today, we've just had our welcome address. We're going to have a brief introduction to the journal. I'm going to introduce our speaker for today. We're very lucky to have Dominik with us today. I'm going to touch on a few housekeeping rules for our events, followed by the approximately 20-minute presentation, your questions in our question time, and then some information on the next event and our closing remarks. So the information on the journal. Hopefully everyone is already familiar with the journal Resources Conservation and Recycling. I like to think that the research interests of our journal are fairly well represented in the name. We are interested in everything to do with resources, conservation, and recycling. Specific points of the scope that are of interest to us: systems-wide strategies, technological, economic, institutional, and policy focus, resource management practices, conservation, recycling, and resource substitution, resource productivity improvement, restructuring of production and consumption profiles, and transformation of industry. In terms of our housekeeping, if all communication could please be in English. This is just so that we have a bridging language that we can all use to communicate with each other. If you would benefit from closed captions, they are available to you both in the Zoom environment and also on YouTube. So if you're one of those people that would like to watch this webinar muted without audio and you want to read the text, or perhaps English is not your first language and you might benefit from some subtitles, some captioning, please feel very free to use it. It's available there for you. If you have any questions, please feel very free to post them in the Q&A over the course of the presentation or during the Q&A time. And if you see a question there that really piques your interest and you would have asked the same question, be sure to upvote it so we can get to it a little quicker than the others. We also offer the opportunity if you would like to ask your question in person directly. So we do have the capability for you to speak directly with Dominik today, using your microphone or microphone and camera combination. All you need to do if you would like to do that during the question time is to use the raised hand reaction in your toolbar. And if time allows, we would be more than happy to have you on the floor with us, having a chat with Dominik. So an introduction today to Dominik WIEDENHOFER from the University of Natural Resources and Life Sciences in Vienna, also known as BOKU. He's going to be speaking with us today on mapping material stocks of buildings and infrastructure around the world. The research by Dominik WIEDENHOFER aims at understanding pathways towards a sustainable circular economy, as well as the necessary structural conditions for a sustainable everyday life with high well-being. For these purposes, he develops biophysically consistent systems models of the socio-economic metabolism, aiming to assess the environmental benefits and trade-offs of supply and demand side measures and their well-being implications. He pioneered the dynamic modeling of economy-wide material stocks and flows at national to global scales. In 2022, he was identified as one of the top 1% highly cited researchers globally by Clarivate. Dominik WIEDENHOFER is the founder and co-chair of the Sustainable Circular Economy section of the International Society for Industrial Ecology. A pleasure to have Dominik with us today. So without further ado, I will turn you over to him. Thank you, Dominik.
Thank you very much for the nice introduction and for having me here. Now I will not mess up my screen sharing part. That's looking good. All right, so welcome everyone also from my side. Very happy to be here. I was originally invited because of a paper I recently published in RCR, and I offered to give a little bit of a tour of the whole mapping stocks field and not only talk about my one paper. So bear with me. I hope this is still interesting for everyone. So firstly, the why. So why are we even interested in material stocks? Well, they form the biophysical basis of production and consumption. They're the built environment that surround us, that shape our practices, that shape our behaviors, that shape our options, what we can even do in everyday life. They also constrain the paths that we could take into any kind of energy transition or transformation of production and consumption systems, because simply speaking, we cannot just replace our cities and infrastructure networks tomorrow. So we have to live with what is already here and see how we can transform this into more sustainable pathways. And stocks also constitute a reservoir of future secondary resources. So basically the whole urban mining debate enters here, basically saying that why not use the resources we already have in use whenever they come to the end of their life? Let's try to recover those instead of opening ever more primary resource mining efforts. And one of my great colleagues, Maud Lanois, draw this very nice picture about stocks, so that the tree is basically the built environment, which branches out into all kinds of details that you can think about, be it specific buildings or specific infrastructure types. And in the end, we all want the fruit of well-being for everyone. So this is kind of the framing idea here. Okay, so this is kind of a very big scope. Today, I'm more focused on mapping stocks. Why am I also doing this? The second why, most people might have seen this kind of chart. So basically, if we look at resource use over the last 150 years, it has been increasing rapidly and very steeply, and it doesn't stop increasing. So this is a big part of our sustainability problems. If you look at the central part, you will see that material stocks are also increasing rapidly, very much in line with GDP growth, very much exponential trends here. So a lot of the, basically more than half of the resources that we extract end up in stocks. So one might wonder where they are. This brings us to the mapping part. But also, just to close the argument here, obviously, whenever we use resources, that also means energy, that means wastes, that means emissions occurring. So this stock flow consistent perspective on our socioeconomic systems, I think, is really helpful to understand the dynamics we are faced with. Let's move into the mapping part. To really understand urbanization, spatial planning, urban mining, all of these issues, we actually need spatial information. Only national level information is not that sufficient. We actually want to understand how does the built environment look in space? How does it change? Where do certain things happen or don't happen? And intuitively, one would think we have all played around with Google Maps. You can see everything there, so what's the problem? But these are pictures, and people are very good at interpreting pictures, but computers are not, per se. You have to train them very hard so that they can actually make use of any of that information. And this is where this mapping of stock efforts comes in. So you actually want to have information on how much land is basically sealed by infrastructure, by buildings. You want to know the heights, the types. So is it a factory? Is it a residential building? All of these things you want to know. You want to know if there is a highway or a local road or maybe a tram line. These have very different implications on the types of materials contained in them, so the stock. And obviously over time and across countries, these things can be quite different. So these are construction and architectural styles, which are obviously not that homogeneous around the world. And therefore kind of local specificities also feature in. If we want these kind of maps to be useful, we want to have them with high spatial and temporal resolution. We want to have high granularity, basically a lot of information on types, components, end users, age cohorts, qualities, all kinds of things would be wonderful to know. And the challenge here is that there is various data out there. So on the right-hand side, you can see the nighttime lights around Europe, which already give you an indication where stocks might be. On the top side, you see a 3D building model from some German districts, which also gives you a lot of information. So we see bits and pieces, but putting them together is the actual challenge that I've been working on a lot. And just to give you this introduction into the field as well, actually a lot of this work goes back to Professor Tanikawa, who pioneered this mapping of stocks with his so-called 4D GIS approach, which is very historical, very local, and very rich in information. And I think this kind of work has kind of developed for quite a while now. By now, we have maps of cities around the world. So I'm giving you a quick example of what happens if you do these 4D GIS things. This is a city in China. And now the interesting thing happens. This massive urban transformation from an industrial to a residential city really becomes visible. And you can derive a lot of information on the kind of amounts of waste, on the types of buildings, also on the lifetimes, and a lot of really valuable information. As you can already notice, probably this is going to be really hard to do for an entire country. So this kind of approach is inherently limited to basically an entire city is already a lot to do. So the studies that are out there usually go for parts of cities, and only for Japan, such a map actually exists for the entire country. Other people tried other approaches. So another one is using local mobile sensing. So this is kind of like the Google street cars that we have all seen driving around. You can do such a thing also with other sensors, which gives you actually potentially a lot of great information. So for example, you could also assess energy efficiency of buildings with it. The problem is this is also very data intensive, and it has quite a way to go before it becomes robust. And again, relatively more regionalized approaches. Now we move into the more kind of remote sensing approaches. Some people might have heard about LiDAR, which is basically a radar scan, highly detailed of the entire surface of the planet. And people are starting to use it to look at parts of cities, basically, and to also use aerial photography. Very, very data intensive efforts. LiDAR data is very expensive, tough to handle. And again, it's in the early phases, and I'm not sure how far you can upscale these kinds of approaches. And in my work, I'm very much interested, as was mentioned in the introduction, into this kind of more systems level, macro level perspectives. So luckily, we had a big project where we said, well, why can we not do this at the national scale? And why can we not do this at the global scale? This has to be possible. So we set out, and one approach that is out there, and colleagues are developing that one, also published in Resources Conservation and Recycling, is going with the nighttime lights. So here you see an aerial photography, and you see a little bit of a picture how the city might look. If you look at the nighttime lights, you can already assume, well, there has to be a correlation, isn't it? If there is buildings, there is light, so you can actually start to work with that. And people have produced very nice maps with that. The inherent problem here is, as you can imagine, the maps look really cool, but the spatial resolution is quite limited. Nighttime lights give you data on basically 1 kilometer grid sizes. So this is quite rough. For big picture stuff, it works well. And you can also imagine that buildings with a lot of light might be visible very well, but what about all the roads on the countryside, for example? What about if cities change their lighting systems to LED to save energy, then suddenly the whole nighttime light picture looks different. And smart people are working to address those, but we were not really satisfied. We said like, well, the European Union spent a lot of money to bring up the new Copernicus satellite mission. We should try to use that. And now, finally coming to what I'm actually doing myself, we developed a new method drawing on this newest generation of satellites from the Copernicus mission, which actually give you data at 10-meter resolution and actually globally. With this kind of information, you can do a lot of things, and you can also map out all the sealed surfaces on the planet. You can actually use radar information to derive building heights. And if you bring in typologies of buildings and material intensities, you actually get a map of material stocks at very large areas. So this was the original paper where we developed this. Oh, and yes, OpenStreetMaps was very helpful to cover some of the line features that a satellite is always struggling with to recognize. To make this a little bit more intuitive, how does this even work? So we have these satellites, which basically fly around the Earth every 5 days. You get a full picture of the entire planet. You can imagine the amounts of data that you get from that. There you have to remove all the cloud cover. You have to remove a lot of distortions. And that's a lot of data work. And there is very clever people out there trying to make this better and better. We luckily had great colleagues working with us on this who are specialists on remote sensing. With these kinds of maps, you already have a very good starting point. But we thought like, okay, but obviously the height of the building is really important. You don't only want to know about how much area is sealed. You want to know how tall are the buildings. And for that, there is another satellite from the European Space Agency, which actually has radar. And radar is a nice thing because actually it's not bothered by clouds. And secondly, you can basically use the radar shadow that goes back into space to derive height estimates of buildings, which works surprisingly well. And if we put all of this together, we have these 10-meter resolution Sentinel-2 data, we have radar data, we have OpenStreetMaps. And we put this all together. I'm not going into the technical details, but basically we have a machine learning regression approach to identify for each pixel, each 10-meter grid size, grid cell, what's in there. We have a support vector regression model to estimate the building heights based on training data. Training data is always needed. And we can also derive the building types based on a random forest classifier, again, using also building types. So this is kind of already moving a little bit into this artificial intelligence, big data space, but we did not want to overdo it because we still wanted to actually understand what's going on and not just get something out of the machine. And as every country, every region is always a little bit different, in most cases, we actually collaborate with national experts. Because, yeah, every building can be different and every country does it differently. So you need to really understand what type of buildings are there and how they are constructed. What does high resolution even mean? Why is this important? And I think this visualization makes it really clear. This is the same area at 10 meters, at 100 meters, and at 1 kilometer resolution. And the 1 kilometer is what nighttime lights usually do. So you can already see you lose a lot of insight and information and possibilities with this kind of data if you have varies like 1 kilometer or higher resolution. And if you go to 10 meters, yes, there will be errors, obviously, but you get much closer to what can be used for various purposes. So I think this is really a big advance that we managed to do here. And after this first methods development proof of concept approach, we basically rolled this approach out to various countries. So we have the original paper. We even created time series for Germany using also Landsat, which is the oldest satellite mission that we have going back to the 70s. We mapped out the United States. We mapped out a big area in China. And the paper that I was invited for gets the biggest space, which is the UK and Ireland. As you can see, it's basically always the same group of people, and we divided up who is leading the work on which country. For the UK, I was really proud to have a bunch of great people working in the UK on buildings and infrastructure collaborate here. That makes these kind of efforts really much more useful if you have people very knowledgeable about national or even local circumstances. So here you can see the entirety of the Republic of Ireland and Great Britain. You can see, well, not surprisingly, around London, we will find a very large stock. Think about all the skyscrapers. That's this kind of pinkish spike that you see there. That's the City of London, the iconic one. But what I've also found interesting is to see this kind of medium density building settlement types that we all know from movies, maybe about the UK, you know, these terrace houses look all very cute. And basically that's what most of England has, a lot of them. And you see a lot of roads also. So you see this combination of infrastructure and buildings needed. Interestingly, for Ireland, we even already here see a much denser road network that they have created to use the lands, basically. Okay, so that's already a nice picture. What else can we do with this? So if you zoom in, you get all the detail that you might want. So here, for example, in the bottom row, you see also these very strong lines are actually subway lines, which usually have very materially intensive. And if on top, you usually have roads. So this kind of adds up from this kind of spatial perspective. You already get some indication about different types of city structures. So London looks quite different to how Manchester and Liverpool looks like. And I think using this kind of data, a lot of exciting next steps will be possible to think about spatial patterns of settlements in a much more coherent and systematic way if you have consistent maps, basically. We can also quantify the amounts of materials stocked in all types of buildings, materials. I'm not going into the details here. Basically, you see that the UK has nearly 18 gigatons of materials as in-use stock, whereas Ireland only has a little bit more than 2 gigatons. On a per capita level, they are much closer, but you already see some differences happening there. I took it a little bit further because I I'm not a real geographer, but I was always intrigued by this question of how does urban form actually relate to resource use, and how does it relate to the amount of infrastructure and buildings we have. We all might have this intuitive feeling that a single family house is very inefficient and a multifamily residential building is much more efficient, which it actually is for energy flows and things like that. But if you look at the top left chart, you actually see building stocks per capita per area across population density of all regions in the UK and Ireland, okay? So that's a lot of colors, but basically what you're seeing is that for nearly all population density gradients, the building stock per capita is actually very similar. So yes, the single family house needs more space, but there is less people in it and actually not that much material. If you have a skyscraper, you have huge amounts of material and you have huge amounts of space, which is not useful floor area actually, because you have elevators, you have hallways, you have all kinds of facilities in there, which in the end don't make these types of buildings that much more efficient, especially if you figure in that there is not just residential buildings, but also various other buildings that we need in our everyday life, like offices and hospitals and shops and whatnot. So I was quite surprised to see that only at very, very low population densities, we find a really high stock per capita. Very little people living in like remote areas. But for the rest of the UK and Ireland, it's actually really flat. And I was surprised. I always thought city center living has to be more efficient. And it actually is for a lot of energy flows, greenhouse gases. But for the stocks in the UK and in Ireland, surprisingly, it's, well, one could say the spread around the box plots gets a little bit more tighter, so to say. But, well, in the end, very similar pattern. But what we actually save on, and that's the bottom left figure, is all the per capita mobility infrastructure. And that intuitively also makes sense. In a city, you need much less roads and much less sideways and all kinds of other stocks in your mobility infrastructure to give people the access to mobility services, basically. Whereas on the countryside, we have much more roads, just connecting areas, roads used for agriculture, for forestry, all kinds of things which make them, in a simple per capita perspective, much more stock intensive. So denser living basically helps you to save on infrastructure, but not really on buildings, at least in the UK and Ireland. And I found this quite interesting. What else do I have? Well, yes. So that was the UK effort. We actually, just today, I got the email that we have a global mapping accepted. So working with the German Aerospace Agency, we have a 90-meter resolution global map of all buildings around the world. That was very exciting, a big first step, but lots of room for improvement as well. But I think this kind of high resolution mapping space has really moved forward a lot. To look at the last piece of my presentation, you can also do this for infrastructures, because OpenStreetMaps actually, surprisingly, has become a really good data source. There has been great work on the completeness and accuracy of OpenStreetMaps, and it's actually really, really good. For most places around the world, you have relatively good information, except for China, who basically, they stopped or they basically banned people to input information into OSM. So whatever you find in there right now is just a snapshot of the past. It's not really evolving anymore. But in all other places, you can actually do this. And I think now we basically have these high resolution infrastructure maps. We have high resolution building maps globally, consistently. And this really allows us to take all of this work a step forward and think much more about questions of urban form, future urbanization, which types of spatial patterns of settlements actually allow us to live more resource efficient lives and might help us to mitigate the climate crisis. To sum up, I have shown you 3 approaches which are more local regional. Basically, I would summarize, if someone works, for example, with a municipality, these kinds of approaches make a lot of sense because they are very close to what's on the ground. They are very close to official information. More and more cities actually have 3D city models that they are making available, which still require a lot of work to be kind of useful and robust. But if you're locally interested, if you have local stakeholders, these are really great approaches. If you're looking at more macro level issues, maybe national level policy, maybe global analysis, I think this research space has really evolved rapidly, as I argued. So nighttime lights are doing interesting things. And with our new method based on Copernicus satellites and OpenStreetMaps, basically we now have as much resolution as you want. 10 meters and below already becomes such a burden to handle in your computational environment that this is actually more than enough resolution, I would argue. One can always improve on training data. One can always improve on other factors used in these calculations. But I think this is really tremendous progress and a lot of excitement I'm hearing also from colleagues in the UK, where I presented the UK-based work to the Circular Economy Roundtable, where a lot of actually stakeholders and practitioners were really happy to see this kind of first order estimate of what's out there to help them a little bit plan their strategies. So a lot of useful applications coming up. The last thing I want to mention is that no matter which approach, so-called material intensities, so how much material per type of road, per type of building, per type of whatever you're mapping, that kind of thing is actually the huge weak spot in all of these things, okay? So we have a lot of information. We need very detailed information. On the left-hand side, you can see the typical building. There is actually ISO standards how to define what is useful floor space, to look at the wall sizes, to look at all of these things. The literature is slowly making this more explicit, but it's tricky to have good data on this. If you look at the right-hand side, you see these not very good drawings of a building. These are mine. I take all the blame. Basically, what I'm trying to say here is the high resolution mapping I introduced, the satellites only see cubes, basically. They don't see the below ground part. And you have to make this approximation of how does building volume of a cube relate to the actual useful floor area and the materials in that building. So there is always these translations when bringing research streams and methods together, where one has to be really careful and one has to really look out for the fine differences. And here I'm advertising some work by some great colleagues who are actually building big databases on all types of buildings and their structural the materials contained in those buildings. By now they have data for a lot of buildings around the world. I think an update is coming out soon. So I think again here the community has really come a long way, and I think it's important to go for the newest information if you plan to use any of it, and be really careful about the assumptions you put into these small issues that you see sketched out here. Okay, coming to an end. I would say there has been a rapid evolution of the field in the last 20 years from mapping specific districts in a city to now global scale maps. All of this requires really interdisciplinary communication and collaboration. So it took us years to establish a good relationship with the remote sensing colleagues and to really understand what each approach can and cannot do, which are the things that people are excited about, which things they might be less excited about, to build these bridges between also architecture, urban planning, industrial ecology approaches, and to kind of leverage the strength of all of these approaches. It takes a while. It's not entirely straightforward, but it's very rewarding. We are also at the point where we see by now a lot of different material stock estimates in the literature. I think the challenge here now is that they are quite inconsistent. So we compared those around the world. There is a factor 3, 4, factor 10 partially differences in stock estimates for the same region and same type of stock. So I think now that the field has really evolved into this whole depth, it needs to come to a little bit of a more coherent understanding about the world. Because if we want to mitigate the climate crisis, if we want to have a more circular economy, which actually helps us with sustainable development, we also need a very good understanding of the baseline situation. And if we start out disagreeing about the baseline, what are we going to really say about the future? So I think there we have a way to go. This brings us to variable system boundaries and lacking documentation. Whenever I'm talking about all of this, I'm complaining about open science and fair data. I think it's really important that we become more open, that we give out the data. So for example, our work always has full access to the maps via repositories, full documentation of all the procedures, so people can actually adapt them and use the parts that they find useful. So one might, for example, take our maps and say the material intensities are not what we need. We just take ours, or we take new ones and put them into the maps that we created. So one can build on these kinds of efforts. I think we really need more cumulative efforts basically out there and build on each other's efforts. Well, and I think I'm really looking forward to the next years to see what happens with all of these great new data sets that we were working so hard to have. And now it's time to actually make more use of them. And with this, I'm saying thank you.
Thank you so much, Dominik. Such an interesting presentation. I found it absolutely fascinating, and also an inspiring call at the end there for some more openness with data sharing, which I think is important across all disciplines. So it's actually very timely that you happen to be giving this presentation, because I was actually just reading an article of the other day. So being a person that doesn't know a lot about circular economy, but I believe that a common critique of circular economy principles is that it is often material flow based and doesn't take into account stocks. Is that right?
Yeah, thank you. That's a very important critique that I actually support. I think there is, at least in the European mainstream discussion, a lot of focus on what I would call small products, like, I don't know, washing machines and dryers and cell phones, which is all important to, handle better. But if you want to do something on climate change mitigation, for example, you need to look at buildings. You need to look at construction. You need to look at infrastructures. And there, I think the much more powerful leverage point that we have is to adapt what is already out there. And in the circular economy world, you would call this extend the lifetimes of these stocks, renovate, refurbish, repurpose, all of these things which make use of what is there and make it more fit to the future, basically. So, which is a big challenge also for the construction industry, because they prefer demolishing and building anew for many reasons. It's not malintent, but there is many good reasons out there. But I think if we really want to have a chance of achieving 1.5 or 2 degrees of climate heating, or to limit climate heating to that range, we have to focus much more on what is already out there, and that's what the stocks are. And to make do with them, basically, especially in, let's say, the higher income countries that most of us probably live in, where population growth is rather low. We already have a lot of unused space. We have a lot of, let's say, not optimally distributed and not optimally used buildings and types of infrastructures. So I think that should be much more important. And yes, obviously, recycling is wonderful and great and important and relevant, but we cannot just recycle everything. Thermodynamics tells us this cannot work. Energy requirements will explode. So this is not the way to go. The way to go is to make use of what we have already, and only what we really need to demolish, that needs to be recycled, no questions asked. But moving away from these flow-centric and maybe more exciting things to the actual big hitters, which is construction, and which are metals, basically. Construction and metals, that's what matters for climate.
Very nice. Sorry, I should mention that if you do have any questions, feel very free to post them in the Q&A now. We have the Q&A now. So Dominik, maybe you did cover, just this is actually more for my personal interest than anything else, but you did cover sort of a brief history of this mapping. You talked about the different methods. I think you mentioned 6 different approaches there. Maybe you could just give a very brief timeline of how old this sort of concept is, how exponentially you think it's grown compared to other research areas, the latest data, how much better each step has been compared to the previous step, and where you see it going in the next couple of years.
Very good question. So the foundational papers are basically from the mid-2000s. So the first 4D GIS paper, which actually was on a little part of Manchester, that was published in 2009, and the actual work happened years before that. We know how it goes. The first nighttime light estimates published in PNAS back then, I think that was 2009 also. So we basically have like 15, 20 years of evolution or of the development of this kind of field. And my feeling is that basically the last 10 years, or actually the last 5 years, where things are really exploded, because basically the 4D GIS approach with census data became really strong because more and more open 3D city models are becoming available. And this whole digitalization of the census information that actually cities have, I mean, cities usually know which buildings are, or approximately what they allowed to be built. What really happened is a different thing, but at least what the permits tell us, they have relatively good information on that. And more of that is becoming digitally available, which actually makes any of this so much easier. So I know Professor Tanikawa quite well. He actually spent lots of time in archives looking at historical maps. And you can imagine that this is very labor intensive. And when it comes to the more large area mapping approaches, I think the big boost basically is just happening in the last 5 years, because the Copernicus mission from the European Space Agency, these kinds of satellites started transmitting actual data around 2017, 2018, when the first data came in. And that's what allows you to do large area 10-meter resolution work. Before that, you have Landsat, but Landsat is much more coarse and has much less bandwidth areas, so much less information basically to work with. So I think the really nice large area things just recently became possible, basically. And the same goes for OpenStreetMaps. I mean, 20 years ago, OpenStreetMaps started, but I think that it's becoming an actual data source that is useful and comprehensive is already probably also only the last 10 years or so. So the curve is really steep, I would say, how the field develops. And more people are moving in, more and more people are really interested to understand stock dynamics. And my feeling is that I think we will see increasingly more work, firstly on kind of big picture evolution, how we urbanize the planet, how we seal surfaces, how we change the face of the earth, basically, in the way we build our cities, settlements, and infrastructures. I think we will get much deeper understanding here. A lot of previous work is usually constrained to a handful of big cities. And when it comes to the more local area approaches, I think now more and more municipalities are becoming really aware that they need to do something about their built environments, also from a resource and climate change mitigation perspective. And I think there we will see a lot of progress. So I know various people working with specific, their own cities, so to say, a lot of information coming from administration, close exchanges with stakeholders. So I think this is also really exciting. And to me, it just shows that none of these methods is superior. It depends on what you want to do. And it depends on your target audience, so to say. And I think there now we have this really nice spread of options, how to move forward, which things to do, depending on what you actually want to achieve. And that's really great.
You talked about the sort of early points of this field coming from, say, for example, archive data from, I assume, councils and things like that. So is that still something that's, I mean, that sounds very labor intensive because I suppose all councils have different ways of documenting it and potentially the methods of documentation change over time. So is there some kind of central database for this, or is it really, when you do this kind of research, you can use the satellites, you can use the street view and these sorts of things, but actually it does also come down to still going through, manually going through, for example, council records and things like that?
I think the manual part is, if you want to do local area work, you need to do the manual part as well. So great colleagues of mine spent their entire PhD looking at records for one city to reconstruct that city's built environment evolution. And I think there is no real way around it, because more and more cities are doing this open city model, 3D models. But that's, to my understanding, that's usually bigger cities and usually higher income cities. So a very specific part of the world. So as soon as you want to go, for example, to the global south, where much more dynamics are going on, none of that information exists. And, you know, you have all these informal settlements, unplanned structures, a lot of things which are much more difficult to grasp. If you look at the more high income settings, I think the archives give you a really important feedback. So for my city where I live, Vienna, I talk to people doing this very specific thing for Vienna. And basically, they also spend months and months of labor time to harmonize the 3D city model, because even that one is not consistent. And the types of information in there is not necessarily for the purpose of resource management issues. So you have a lot of overlaps and a lot of inconsistencies, and you need to clean this up as well. You know, so this kind of what I would call consistency issues are really important to tackle, even if they might not be the most exciting part of the work. But robust information is something that we as scientists, I think, should be very aware of and very careful about.
I mean, with this kind of mapping, because it's such huge areas and based on the kind of data that you're able to obtain, I guess anyway, there's a lot of error. So I suppose the more time you invest in actually going through these kinds of records and things like that, the better your accuracy is going to be, I suppose.
Yes, absolutely. So, for example, for our approaches, we always had several research assistants doing basically spot checks, which might mean, for example, sitting there with Google Street View, cruising through the streets of a city and checking if what the algorithm tells you is there actually is there. And you cannot do this everywhere, but you can do this in a stratified sampling strategy, basically. So you need these human quality assurance mechanisms. I also know about people doing maps on China, and they just send out hundreds and thousands of people to do real, like physical on-the-ground checking.
Wow.
And that's really necessary to establish the baselines. I think now it's about what is really robust baselines in there. How can we minimize the error? What are the actual uncertainty ranges as well? I mean, we all know that you can create error bars for everything, but what is a sensible way to create uncertainty estimates, and what is the actual uncertainty? Because, well, you can imagine if you work from satellites to construction guidelines, there is many things that can make this more complicated. And the more local you go, the more these errors might become a problem. So I think that's, again, robustness and consistency is really something to look out for, and to be aware that you definitely need substantial budget or time resources or both to make sure that your baseline estimates actually make sense.
I suppose it would be a hard thing to do, but if you had to sort of just provide some kind of ballpark estimate of the sort of uncertainty and error that we're talking about in these kinds of studies, is there something you could say about it, actually?
Well, I mean, we tried for our own mapping. We didn't really all the way make it, basically, because it became too complex. I would say something like plus minus 30% easily. And if you go, I'm talking about sums now, sums of countries. If you go into specifics, there will be lots of mismatches because classifying the type of building that is there is actually really tricky. So there will be these misclassifications, and then there is this additional thing that we always like to have mixed uses. And that's something a satellite cannot detect, basically. We tried this for several countries and places, but there you basically need ground truthing, you need census information, zoning information to make any of that kind of graspable, because yes, we all know the buildings with shops in the first floor, and then apartments in the upper floors, and then maybe a bar on top, and all of this might have influences that you might be interested in, depending again on what you're aiming to do.
So I was really interested, Dominik, so you have these images and you have the top, like the profile in terms of the height profile. How exactly do you figure out, or estimate how thick a wall is, how many rooms a house has, what is the house made of, like what is the composition of the building? Is this sort of, you talked a little bit about this material intensity data, and I guess it's all sort of brought back to this in this floor area that you were talking about or something, but maybe you can provide a little bit more information about how this kind of stuff is actually estimated or averaged out, or...
So basically there is several steps in there. So the first thing is that the satellites give you information on the building, yes, no, basically, and then you do height estimates. And if you work with national experts, they will very quickly tell you that there is construction rules and guidelines. So for example, above a certain height, it has to be steel, reinforced steel concrete. And that already gives you an indication. And then if it's below and you classify it as a residential building, typical single family houses are built like this and not like that, basically. So you get this kind of height already gives you some indication. And then there might be structural information. So in each of the papers in the supplement, we usually give kind of Google Maps images and say, this is how this archetype that we are using looks like in reality. So imagine a dense city with all the buildings packed together. The satellite sees that this is different to maybe these more Le Corbusier style high-rise buildings with lots of space in between. So that already also tells you that this is specific types of buildings that are out there. The one big weakness in all of this mapping is that usually we know nothing about age composition. So you basically can only use, for example, national housing statistics to say what's the average age composition of the stock. You cannot really say this one was built in 1980 and this one in 2000 and this one last year, which obviously from a materials perspective can have quite the impact. This is really, I would say, the core weaknesses of these kind of large area mapping approaches, that this age composition issue is hard to tackle. And some people overcome it. In China, for example, where a lot is built in a very quick time, you can actually say when it was built. But if you look at high-income countries with a long history, it's actually rather impossible to really differentiate. So I think there is also lots of work to do, and I'm very sure that clever people will figure out ways to make this better, basically, from multiple streams of data and merge these things together.
And finally, another question. I was just interested, this nighttime lights method, I didn't fully understand. So it's based on the light intensity in the square, or, and this is
yeah. So I know that a good colleague of mine, he's working on a really nice version, taking care of a lot of the problems that I'm going to mention now. So the research frontier is always moving. But the basic idea is, as you said, the more light, the more stock there should be. And usually you would have some ground truth data to train some kind of, back in the days, it was basically regression models where you would say, we know that there is this type of building, there is this type of other infrastructure there, and we have a few data points, and then you basically correlate it with the intensity of light. That's the basic idea. And nighttime lights, I mean, it sounds a little bit rough, maybe the way I describe it, but I think it's important to see that nighttime lights are used by a lot of people for all kinds of things. If you think about sustainable development in the global south, nighttime lights are actually really useful to see where people are and if they actually have electricity, for example. So there is, I think, interesting connections you could make to other applications of nighttime lights. But definitely there is these weaknesses that usually the resolution is very coarse, and you really need to be careful about the way you correlate light intensity to material stocks and maybe types, but that's already the types, I think, becomes very, very tricky. So that the published work usually just tells you buildings. There is no real differentiation into single family or low rise, high rise, whatever.
What a fascinating area. I'm really excited. I'm going to go and read a bunch of stuff on this now, Dominik. You've really got me interested now.
That's very nice.
So I think, I mean, we're essentially out of time. So I might actually, well, I'm just going to share my screen again and make sure it's the right one. There we go. Yes. So first of all, I want to say a huge thank you to Dominik for inspiring me and being here today to talk to everybody on this very interesting topic. Certainly new to me and very interesting, I think. So thank you so much for coming, Dominik. So then I suppose I should also introduce the next webinar that will occur. So 2 weeks from now, in a fortnight, we will be speaking with John Atkinson from the State University of New York at Buffalo. And he's going to be talking with us on the topic of moving more than waste, the burdens of plastic transportation. That's going to be on Thursday, November 7th, 2024 at 10 a.m. Pacific time. So same time as right now. Okay, thank you so much again, Dominik, for your wonderful presentation. Thank you everyone for coming, and I hope to see you next time.